The study of mineral-microbe interaction is a vast and critically important field that spans the entire history of Earth from its earliest stages to the present day and encompasses scales ranging from atomic-level processes to global biogeochemical cycles. Often referred to within the broader contexts of geomicrobiology or biogeochemistry, this discipline investigates the profound ways in which minerals influence microbial life and, conversely, how microbial activity impacts the geological world. Understanding this intricate relationship is not just key to deciphering Earth's past but also vital for addressing modern environmental challenges and resource needs. The relationship between minerals and microbes is one of dynamic interdependence, where each component actively shapes the environment for the other. The role of minerals in supporting microbial activity. Minerals are far from inert backdrops for microbial life. They provide essential support through both physical and chemical means. Physical protection and habitat. Mineral surfaces and rock matrices serve as crucial habitats for microbial communities, offering physical protection from harsh environmental conditions. For instance, endolithic cyanobacteria are found living within rocks in extreme desert environments like the Atacama, Mojave, and Al Jafar Basin deserts, demonstrating how minerals provide shelter. Studies show that minerals like phyllosilicates can protect filamentous cyanobacteria, such as leptolingbia, from harmful ultraviolet radiation. The concept of the mineralosphere highlights how the specific mineral composition of a location can control the distribution and function of associated bacterial communities. Mineral microniches within the subsurface can even dictate the diversity of microbial populations. Biofilms. Microbial communities often attached to surfaces frequently form on mineral substrates, with mineral ecology influencing their accumulation, composition, and phylogeny. Chemical support, nutrient and trace metal supply. Minerals are fundamental sources of essential nutrients and trace metals that are required for microbial metabolism and growth. Many critical microbial enzymes involved in processes like nitrogen fixation and methane metabolism require specific trace metals like molybdenum and copper. Minerals can provide these elements. For example, molybdenum limitation can impact asymbiotic nitrogen fixation in tropical forest soils, highlighting the importance of mineral sources. Soil bacteria have been shown to produce molybdophores to facilitate the dissolution of silicates and acquire molybdenum. Similarly, copper availability from minerals is crucial for the ecology and activity of aerobic methanotrophic bacteria. Iron, a key element in many biological processes, is also heavily influenced by its availability from minerals. Iron-sulfur clusters, ancient protein structures, are essential for numerous biological functions, including DNA replication. This connection between mineral iron sulfides and biological iron-sulfur clusters underscores their fundamental role, possibly extending back to the origins of metabolism. Minerals can participate directly in microbial energy acquisition through electron transfer processes. Microorganisms can engage in extracellular electron transfer with minerals, effectively using them as electron donors or acceptors for metabolic reactions. Microbes can drive the redox cycling of iron and manganese within minerals, impacting their form and mobility. Sulfate-reducing bacteria, for instance, can utilize solid-phase electron acceptors. Some non-phototrophic microorganisms can reportedly utilize solar energy through mineral photocatalysis, and phototrophic bacteria like Rhodopsidomonas palustris have shown phototrophic extracellular electron uptake linked to carbon dioxide fixation. Mineral dissolution weathering. Microbes are significant agents of mineral weathering in natural environments. This involves processes like acidolysis, producing organic or inorganic acids to dissolve minerals, complexation, releasing ligands that bind to mineral components, and redox reactions. Bacterial communities, including Beta-Proteobacteria, have been correlated with mineral weathering rates in forest soils. Fungi also play a role, with cellular dissolution observed at fungal hypha and spore-mineral interfaces, revealing previously unrecognized mechanisms of fungal weathering. Mineral transformation. Microbial activity can alter the chemical composition and structure of minerals, especially those containing redox-sensitive elements. The microbial reduction of FeIII in clay minerals like nontronite is a prime example, changing the mineral's properties and reactivity. Mineral formation. Biomineralization. Microbes can directly or indirectly induce the precipitation of minerals, a process known as biomineralization. Examples include microbial-mediated precipitation of sulfates like gypsum, the formation of early diagenetic dolomite, and the experimental diagenesis of organo-mineral structures formed by iron-oxidizing bacteria. Biomineralization can lead to the formation of unique mineral phases or structures that are preserved in the geological record. Mineral-microbe interactions have been fundamental drivers of geological events throughout Earth's history and continue to shape global cycles. Early Earth and the origins of life. The interface between minerals and the environment on early Earth is considered a crucial setting for the emergence of life. Mineral surfaces as catalytic hubs. On a dilute early Earth, mineral surfaces provided necessary loci to select, concentrate, and stabilize prebiotic organic molecules from aqueous solutions. Studies have investigated the adsorption of various organic molecules, including amino acids and nucleic acid components, onto common mineral surfaces like calcite, quartz, goethite, rutile, and clays. Chirality and homochirality. A key feature of biological molecules is their specific handedness homochirality. Minerals with chiral surfaces have been explored as potential sites for the selective adsorption or synthesis of one enantiomer over the other, potentially playing a role in establishing the homochirality observed in life. The mineral origins of life. Some hypotheses propose that early life forms or protocells might have originated or been structured around mineral frameworks, highlighting a deep coevolutionary link. Transition metal sulfides, abundant in hydrothermal settings, have been specifically implicated in the origins of metabolism by catalyzing early biochemical reactions. These microbes shaping early geochemistry. Microbial activity dramatically altered Earth's early geochemistry. The evolution of microbial metabolisms, particularly oxygenic photosynthesis by cyanobacteria, led to the rise of oxygen in the atmosphere and oceans. Microbes shaping early geochemistry. Microbial activity. The availability of metals in the Archean influenced the expanding network of microbial metabolisms. Microbial iron oxidation, potentially coupled with early forms of photosynthesis like manganese oxidizing photosynthesis before the dominance of cyanobacteria played a role in the formation of massive iron formations, banded iron formations. The timing and mechanisms of processes like biological nitrogen fixation by molybdenum nitrogenase are also preserved in the isotopic record, linking mineral availability molybdenum to early biological innovation. Microbial activity also influenced the formation of phosphorites and microbial carbonates over geological time. Mineral evolution and coevolution with life. A comprehensive survey of Earth's minerals suggests that about half of all mineral diversity is a direct or indirect result of biological activity and its byproducts. This perspective, termed mineral evolution, highlights how the evolution of the geosphere minerals and biosphere life are intrinsically linked and have co-evolved over billions of years. This approach reveals that many common minerals, like pyrite, fool's gold, can form through multiple distinct processes, some of which are microbially mediated. Each mineral kind holds unique information about the conditions of its formation, including the potential involvement of life, offering valuable insights into Earth's geological history and serving as potential biosignatures in the search for extraterrestrial life. Historically, geochemistry and biochemistry were often viewed as separate, but this new perspective emphasizes the fluid boundary between the mineralogical and biological realms. Hydrothermal systems. Seafloor hydrothermal vents are exceptional examples of environments where intense mineral-water interactions support unique microbial ecosystems. Hot, chemically modified fluids are generated as seawater circulates through oceanic crust, interacting with the rock. These deposits, forming characteristic black smoker and white smoker chimneys, are considered analogs to some types of ore deposits found on continents. The composition of the vent fluids and the resulting mineral deposits depend on factors like the initial fluid composition. Different types of hydrothermal systems exist depending on the underlying rock type: basaltic vs. ultramafic and tectonic setting. Microbial communities thrive in these diverse vent environments, often within the mineral structures or the subseafloor, influencing and being influenced by the fluid chemistry and mineralogy. The longevity of hydrothermal activity at certain sites, lasting tens of thousands of years as indicated by dating of deposits at Lost City and Tag, highlights these systems as persistent sites of mineral-microbe interaction. The unique geochemical and physical conditions of hydrothermal vents, particularly those hosted in ultramafic rocks producing hydrogen and methane, are also considered prime candidates for potential sites for the origins of life. Carbon cycle impacts. Mineral-microbe interactions are critical components of the global carbon cycle, particularly through rock weathering and carbon storage. Terrestrial rock weathering is a fundamental process that slowly removes CO2 from the atmosphere over geological timescales. Climate models examining the carbon cycle implications of weathering changes since the last glacial maximum show that increased weathering fluxes transfer substantial amounts of carbon and alkalinity to the ocean, leading to atmospheric CO2 drawdown. The expansion of vegetation, which enhances microbial activity in the rhizosphere and thus weathering, introduces significant uncertainty in models because different parameterizations treat this biological enhancement differently. Furthermore, the balance between carbonate weathering. This balance is influenced by the spatial distribution of rock types, underscoring the need for geographically explicit weathering models to accurately estimate carbon cycle impacts. Beyond weathering, mineral-microbe interactions are also central to the formation and persistence of soil organic matter. Organic matter associations with minerals are a key mechanism for long-term carbon storage in soils and sediments. Microbial processes can also contribute to carbon sequestration through the engineered carbon mineralization of ultramafic rocks, potentially offering a pathway for removing CO2 from the atmosphere. The intricate interactions between minerals and microbes offer numerous opportunities for practical applications across various industries and environmental challenges. Resource recovery. Microbial processes are harnessed for the extraction of metals from ores in a process called bioleaching. Environmental remediation. Microbes are powerful tools for cleaning up contaminated environments. For example, microbial reduction of iron in clay minerals can be coupled with the degradation of organic contaminants. Microbe-induced mineralization can be used for soil solidification and stabilizing heavy metals within mineral matrices. Agriculture. Mineral weathering bacteria can be used to enhance nutrient availability in soils, potentially reducing the need for synthetic fertilizers. By promoting the release of phosphorus, potassium, and micronutrients locked within soil minerals, these microbes can improve crop nutrition and support more sustainable agricultural practices. Carbon capture and storage. As mentioned, microbial carbonation can accelerate the process of mineral carbonation in rocks, offering a potential biological pathway for capturing and permanently storing atmospheric CO2 in solid mineral form. Construction. Microbial processes, such as microbe-induced calcium carbonate precipitation, are being investigated for applications in construction materials, like creating biocement for soil stabilization or concrete repair. Despite significant progress, the study of mineral-microbe interaction presents grand challenges and numerous opportunities for future research. Accurately modeling the complex, spatially variable interactions, especially over geological timescales and in response to climate change, remains a challenge. Further research is also needed to fully elucidate the mechanisms involved at the mineral-microbe interface, understand the full breadth of microbial metabolisms linked to minerals, and optimize these natural processes for biotechnological and environmental applications. In conclusion, the dialogue between minerals and microbes is a fundamental force driving Earth's evolution and maintaining its biogeochemical cycles. From providing the physical scaffolding and chemical fuel for early life to shaping landscapes and influencing global climate today, these interactions are integral to Earth science and offer innovative solutions for resource recovery, environmental protection, and sustainable development.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 650 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 1,800 Earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.